Today's lecture is about soil formation. This is typically the beginning of any geotechnical course, and what I would like to emphasize is that this is much more than just an intellectual exercise or going back to the classes in geology. This is a critical component in understanding how soils behave. Tell me how they form, and I'll be able to anticipate so many of their properties and behavior upon loading or wetting in the future. Now, interestingly enough, soil formation starts by understanding rocks. So today we're going to start by talking about rocks. Then we're going to see how rocks weather and degrade, and some of those components may be transported or they may remain in situ, giving the origin to residual soils or transported soils. So let's get started. The typical triangle that summarizes the various rock formations is schematically shown here, where we have igneous rocks. That means there is an association with fire, with heat. Sedimentary rocks, that means that they have formed by sedimentation processes, and a little bit more complex than that. And these two can transform with pressure and temperature to become metamorphic rock. Let's start with sedimentary rocks. The typical one that it relates to the concept of sedimentation are those that form that become mudrocks and shales. These two words are typically used interchangeably. However, there is a fundamental distinction between them. Shales have become fissile. In other words, if you knock it, it will tend to split in layers. This is not the case of mud rocks. But in any case, these two types of rocks are basically made of carbonates, silicate, clays, and organic matter. Therefore, shales are not only seals because they have very low permeability because of the clay content. They are not only good seals to store hydrocarbons beneath them, that is the typical caprock for most of our hydrocarbons. However, shales are also source rocks because they have trapped the organic matter, a few percentage, but that is enough that at sufficiently high pressure and temperature in this pressure cooker beneath the surface, gas can be generated, leading to the shale gas revolution. Once again, because of the presence of clays and the particle alignment during sedimentation and overbearing, and also because of the organic matter that gets stretched, the two come together to give the fissile behavior of shales. As I said, the word sedimentary, it can be misleading. It doesn't mean that they are just sediment. Evaporites, a case in point. If you take water and salt and you mix it so you dissolve the salt and then you leave it on the countertop to let it dry, you'll come back tomorrow and you'll see that the soil has reprecipitated. This is the way evaporites are formed. To give you an idea, for every meter of salt rock, that means that there must have been 7 or 8 meters of seawater that has evaporated. Now take that further, and in many parts of the world we find kilometer-thick layers of salt. That means that 70 kilometers of water have evaporated in the formation of those layers. Now, when those layers form, there was also wind carrying fine particles, and so sometimes they are not that pure, and there may be layers of silts and sands interbedded between the salts, and as well as organic matter. So in many cases, the salt itself may hold some hydrocarbons. But in general, the evaporites, because salt is very creepy, it will deform and it seals the porosities. Evaporites are wonderful seals with virtually zero porosity. So we may find lots of organic matter that trapped beneath the evaporites that has eventually converted into oil and gas. So we find evaporites beneath the Great Lakes in the northern USA and Canada because Those lakes were originally somewhere near the tropics, and those basins got flooded with seawater and evaporated, becoming these very thick layers 400 million years ago. Or in the Gulf of Mexico 200 million years ago, off the coast of Brazil, where all the new findings of oil reservoirs are found, those are also subsalt, and those formed 110 million years ago, and much more recent in the Red Sea. Before the Red Sea finally opened and it got flooded with seawater, at the beginning water was just leaking in, evaporating, and precipitating salt. Those are 25 million years old, or 20. Once again, these are very thick layers, and you will see a little bit more of that as we talk about soil formation. Carbonates are some of the most important rocks we encounter on the surface of the Earth. Carbonates formed by trapping of calcium from the ocean and CO2 from the atmosphere. For example, microorganisms have played a critical role, and that is the formation of foraminifera, these little spherical shapes which are the exoskeleton of microorganisms that are made of calcium carbonate. Eventually they sediment, they carry with them many times organic matter, and that also has led to the formation of the oil reservoirs. Because there is one more characteristic of carbonates, that they are very sensitive to chemical conditions and pH, but also that they have left a fairly significant porosity in excess of 20-25% in many cases. So carbonates are great storage space for migrating hydrocarbons and also for the formation of hydrocarbons. Most of the oil in place today is encountered in carbonates, but if you go to Florida, carbonates are, and because of karst terrain that has eroded, fresh water from the rain coming in and eroding, creating these large caverns and cavities that are great storage space for fresh water. Carbonates are also a great source of our calcium oxide. In other words, every time we put carbonate in a kiln, we break the molecule, CO2 escapes, we capture the calcium oxide, and that is a critical component for many lime mortars, and in the last 2 centuries for Portland cement. Igneous rocks may have formed by the freezing of lava, the solidification of lava in the subsurface, or during an eruption, lava flows and then hardening at the surface. When igneous rocks form in the subsurface, the cooling was very slow. That means that as soon as a nucleation spot took place, it had time to grow, attracting more reactants to support that nucleation spot. And so intrusive igneous rocks have large grains. And this is the case of granite. However, if it came up to the surface in liquid form and then it cooled up very fast, solidification nuclei start at a large number of locations, and before they grow, a new neighbor crystallizes, and therefore it forms very small grains, and those are extrusive, case in point, basalts. Now, as I said before, either igneous rocks or sedimentary rocks may be subjected to pressure and temperature, and in so doing they will change their form without changing the chemistry. So there is a metamorphosis of the original parent rocks. The common case is limestone under high pressure and temperature becomes marble. So now let me give you 2 examples. Granite has to be in a cooking, isolated from the external conditions, so it can harden very slowly. We say that limestone becomes marble the same at depth, and now we have to wonder, because here in Georgia, for example, we have Stone Mountain, which is a very large dome of granite that we see at the surface, several hundred meters tall. However, it is made of granite, it must have solidified at depth. The same here in North Georgia, we find lots of marble that has been used to make the facades of very famous constructions around the US. But marble must have also experienced high pressure and temperature, pressures in the order of 5 to 10 kilometers deep, and temperatures in excess of 200 to 700 degrees Celsius in that window. That means that in both cases, there was a big overburden that has been eroded to expose the marble and the granite here in Georgia.